This is a lecture for COMP621 Web Security on asymmetric or public key encryption. As you may know from previous lectures, symmetric key or secret key encryption involves encrypting and decrypting with the same key. In other words, the plain text goes into an encryption algorithm with a secret key and out comes the ciphertext. We send the ciphertext across the network or store it in a file. And then later, the receiver takes that ciphertext, runs it through a decryption algorithm using the same key that was used to encrypt it, and out comes the plain text. Plain text, of course, doesn't really have to be text. It can be programs, images, anything, bits or bits. And the most common algorithms used for symmetric key encryption are the DES and the AES algorithms. Asymmetric or public key encryption is different in that the key to encrypt is different than the key to decrypt. They are mathematically related, but they are different keys. And typically, one of the keys, typically called the public key, is made available to everyone so that others can see what your public key is. And then the user or the owner of this key set is the only one who knows the private key. So if you wanted to send me a message such that I'm the only one who could read it, then I make my public key available, I'm user 2, and then you take your plain text, encrypt it with my public key, send it across the network to me, and then I can decrypt it with the private key. And since hopefully I'm the only one with the private key, nobody else can send it to me. Others can send anything they want to because everyone can see my public key, but I'm the only one who can decrypt it. The RSA algorithm is one of the most popular asymmetric or public key algorithms. RSA was developed in 1977 by the team of Rivest, Shamir, and Alderman. In previous semesters, the COMP621 Advanced Algorithms class used a textbook by Rivest, the first of these people. The NSA actually developed this algorithm earlier, back in 1973, but didn't tell anybody because, well, that's what the NSA does. It's interesting to note that because it was developed in 1977, that the copyright or patent on the algorithm has run out and is now in the public domain. The internals of the algorithm are relatively simple. You take a message M, where M is a bunch of bits, and then you raise it to the power E, mod N, where N is a big number, and that gives you the C, the ciphertext. So M is your plain text, C is the ciphertext, and E is a number we'll talk about in a minute. So you raise the message to the power E, mod N, and you get C. Then that's the ciphertext. You send C to the other side, and the other side has the number D, and they raise C, the ciphertext, to the power D, mod N, and you get the message that you started with. So here is the way to form those numbers E and D and N. You start by getting two large prime numbers, which we'll call P and Q, and you multiply them together to get N. So N has only two factors, P and Q. And then you create the token of N, which is P minus 1 times the quantity Q minus 1. So you have to know P and Q in order to calculate this value. And then once you know that, then you choose a value E such that the greatest common divisor of E in the total of N is 1. In other words, E does not evenly divide into N, and there's no numbers that divide evenly into both of them. Okay, now you've got E. The public key is N and E. And in my observation, by the way, E is often the number 64K plus 1. But any value will work as long as it meets this requirement. Okay, once you've got E, then you have to compute D, the secret key. And you do that to choose a D such that D is the inverse mod the quotient N, or D times E equals 1 mod that. In other words, remember we're dealing with mod numbers or rings. And so you want a number that you can multiply times e and ends up with the value 1, or the mathematical inverse of e. Okay, so now we've got D and E and N. You don't tell anybody what P and Q are, and you keep D a secret. But for the public key, you just need to know N and E. Here's an example using small numbers. We have two prime numbers, 101 and 113. So I get out my calculator and I multiply them together, and I get 11,413. So that's N. That's our N number. Now I can figure out the total of N by multiplying P minus 1, which is 100 times 112, so I get 112,000. Okay. Then I choose E to be this number, 3533, which so happens that it has no common multiples. It's the greatest common divisor between E and 11,200 is 1. Okay, so now I've got E. Then I find the mathematical inverse of that. Well, it turns out that the mathematical inverse is 6,597. So there we go. Okay, so now we've got N, E, and D. So let's try this. We choose a data, M, which is 9,726. It's notable that M has to be less than N, because we're going to do arithmetic mod N, and if M wasn't less than N, we'd lose bits. Okay, so now we have M, the data value we want to send. So we encrypt that by raising M to the power E, which is 3,533. So we have to take this number and raise it to 3533 mod 11,413. Now you might recognize that a relatively large number raised to a very large power is going to be a huge number. Fortunately, you can mod it after every time you multiply. So basically, you're going to multiply 9726 by itself 3,533 times. And after every multiplication, you can do the mod in order to shrink it down so it doesn't get too big. Also, there are other mathematical tricks you can do to make the raising it to a power easier. Anyway, when you raise 9,726 to the 3,533 power, mod 11,413, you end up with the number 5761. Okay, so that's your ciphertext, 5761. And if you want to decrypt that, you take 5761 and you raise it to the D power, which is 6597, mod that, and you end up with the number 9726, which is conveniently the value we started with. So that's how it works. Of course, large values of P and Q are necessary. Otherwise, it's relatively simple to figure out what they are. In other words, with the small numbers we have, you can guess pretty quickly. Remembering, in order to calculate the prime factors of a number, you have to test all the prime numbers less than the square root of the number, which isn't really all that difficult. Some people have claimed it's NP complete, but it's not. Okay, so, but it is mathematically challenging. If you use large values of P and Q, it takes an awful lot of time. So we want a big N. The larger N is, the better it is. Of course, N has to be bigger than the text value, because if it's not, then as you mod it, you'll lose values and you won't be able to get the true value of M back again. Okay. Remember, there ain't no good reason for a computer science student to know the details of an encryption algorithm. It is very important that a computer science student know how to select and use the appropriate encryption system. RSA, with all its raising numbers to a very large power, is slower than the secret key or private key algorithms like DES or AES. The secret key algorithms are relatively easy to implement in hardware, and in fact your Intel processor and I believe your ARM processors both have hardware to assist in encoding and decoding the AES algorithm. Not to mention AES can be relatively efficiently implemented in programs. There are hybrid encryption systems that use both asymmetric and symmetric keys, primarily because the symmetric keys work very fast, but you have to exchange keys, and they use the asymmetric keys to exchange a symmetric key. As I mentioned, the longer the key, the harder it is to defeat the encryption system. And you can think about this for brute force. Imagine your key was only 4 bits long. Then with 2 to the 4, 16 guesses, you could try all possible keys and see how ones they work. Now for AES and DES, any bunch of bits will work. And typically they just choose random numbers for keys. Whenever they need to make a key, they just pick a random number and that works. There are some mathematically bad values. If you have 17 zeros in a row or 17 one-bits in a row in the key, it has some weaknesses. So you choose a random number and you see if there are 17 zeros or 17 ones embedded in it somewhere. And a little mathematics will tell you that what's the probability of having 17 ones in a row? Well, it's 2 to the 17, and that's a bigger number. Okay, now that's for AES and DES. RSA algorithm has 2 keys, and not any random bunch of bits will work. You have to carefully pick your P's and Q's. So not every number will work as a asymmetric key. And therefore, they need to be bigger keys because you just can't pick any. Not all 2 to the n possible bits will work for an n-bit RSA key. Now, the DES algorithm uses a miserably small 56-bit key. Triple DES can use 2 or 3 of those keys. If you use 2 of them, it uses just 112 bits. AES, interestingly, has 3 different key lengths, 128, 192, or 256 bits. And RSA can use a variable number of bits for the key. Typically, there are 1K, 2K, or 4K bits in length. I've gone out and bought digital certificates that have keys in them, and they are often 2K in length. Now, once you have an encryption algorithm, you have to use it properly. There are several ways to encrypt data once you have an encryption algorithm. It's notable that most of the encryption algorithms encrypt relatively small blocks of data. For instance, AES encrypts 128 bits, DES only 64 bits, RSA, because the key size varies, depends on that. But typically for 2K, it'd be 255 bits, or you can make the key a little longer and get 256 bits. The simple concept on encrypting data is to use one encryption for each block of plain text. You take a block of plain text, say you're doing AES. You take 128 bits of plain text, you run it through the AES algorithm with a key, and you end up with 128 bits of ciphertext. You do that for the first 128-bit block, then you get the next 128-bit block, and you encrypt that one and get another block of ciphertext, and so forth. This is known as the electronic code book mode, or ECB. It has some problems because 2 identical blocks of plain text will encrypt to exactly the same blocks of ciphertext. And that has to be so because otherwise they wouldn't decrypt back to the same blocks. So using the electronic code book will give you repetitive values in the ciphertext to indicate repetitive values in the plain text. And that can help the cryptanalysis quite a bit. Here's an interesting example. We have an image here. It's like it'd be a BMP image. And then we encrypt it using the electronic code book method. And you end up with values where all the blocks that are one color encrypt to the same value. So if you look at the ciphertext as a picture, you can see the penguin inside the ciphertext. You lose the proper colors, but you can see the image there. It didn't really hide it as well as you'd like. To be secure, not only do you need to use a good encryption algorithm, you need to use it properly. You can use an encryption algorithm perfectly correct and still be insecure. The Cipher block chaining mode, or CBC, is a commonly used system of encryption. This is called stream encryption, in that instead of encrypting each individual block, it encrypts one block, which then impacts the encryption of the next block, which impacts the next encryption, and so forth. So in this example, the plain text is exclusive ORed with the ciphertext from the previous block, and then you encrypt it, and that gives you encryption ciphertext, which is then used to be exclusive ORed with the plain text of the next block, and so forth. So each block determines not only how it's encrypted, but from the previous values of the ciphertext. Of course, how do you start it? Well, you can start it with a initialization vector, which is just a bunch of random bits of the same size as the plain text block. So if you have a 128-bit plain text, you have to have a 128-bit initialization vector. And so this is some random number that you start the whole thing with. To decrypt the Cipher block chaining algorithm, it's relatively simple. You, again, take the ciphertext, run it through your AES algorithm, or whatever algorithm you happen to be using, along with the proper key, and out comes a value which you exclusive OR with the initialization vector for the first block, and it gives you the plain text. Now for the next blocks, you take the ciphertext, decrypt it with the AES algorithm, and then take the result of the decryption and exclusive OR it with the ciphertext of the previous block, and so forth and so forth and so forth. Now, it should be noted that each block is dependent on the previous block. So if there's some error, in other words, if some cosmic cray comes in and corrupts a bit somewhere in the middle of your text, then all blocks after that are going to be corrupted. Typically, though, this is not a problem. There are parallelization issues. Each ciphertext requires the previous block. So if you're going to decrypt block 1000, you have to have the decryption of ciphertext of block 99. The initialization vector is used to encrypt and decrypt the first block of the file. You have to use the same initialization vector to both encrypt and decrypt. The initialization vector has to be sent along with the data so that the receiving side can decrypt the file. The initialization vector does not have to be kept secret, in that if the person receiving it doesn't have the proper key, they still won't be able to decrypt the file. But you do have to have the initialization vector to decrypt it. Typically, the initialization vector is just a bunch of random bits, and most of the time, a secure random number generator is used to create the random bits. If you're sending the same plain text over the network using the same encryption algorithm and the same key, it will be different if you use a different initialization vector every time. So typically most systems, every time they send something, creates a new random initialization vector. That way, if you send the same data, a cryptanalysis will not know it's the same data. It'll be a different bunch of bits when viewed as ciphertext. Now, the initialization vector does not have to be kept secret, but you could protect it with a MAC in order to make sure that it hasn't been corrupted. There are other methods of doing encryption. The Cipher feedback mode is shown here. In this case, instead of encrypting the first block of plain text, you encrypt the initialization vector using your key, and then the result of the initialization vector encryption is exclusive ORed with the plain text, and that gives you your ciphertext. And you take that ciphertext and you encrypt it again, and then take the result of that in exclusive OR with the plain text, and so forth and onward. You can decrypt that by taking the initialization vector, decrypting it with the algorithm, and then exclusive ORing it with the ciphertext from the first block, and that gives you the plain text. You take that same ciphertext, decrypt it with the key, and then taking the result of the decryption and exclusive OR with the ciphertext in the next block, and so forth, and that will give you the result. The Gallus counter mode, or GCM, is another means of using an encryption algorithm. This encryption system is used by Zoom to encrypt the data that's sent over the network. This is somewhat interesting in that instead of directly encrypting the plain text, it takes a counter, initialization value, initializes the counter, and then you increment that counter for every value, and you encrypt the encounter with the appropriate key, and out comes an encrypted version of the counter, which you exclusive OR with the plain text, and that gives you the ciphertext. For the next block, you have incremented that counter, and then you encrypt the incremented counter, and again, exclusive OR the plain text with the result, and so forth and so forth. This is relatively easy to parallelize, because imagine you want to encrypt both the first and second block in parallel. Well, the first one uses the counter incremented by 1. The second one uses the counter incremented by 2. So they can all start with the initial counter, and then depending on what block number you use, you just add that block number to the counter, and that's the value you encrypt and then include it. Many people use passwords with their Zoom meetings and then send the password along with the Zoom ID. It doesn't make the Zoom meeting any more secure to do it that way. There are several other encryption modes that you can use. Each one or many of them have initialization vectors for stream-oriented encryption. Typically, this is not a problem if you just add the encryption vector to the beginning of the file as you send it across the network. Of course, if you have like a 16-byte encryption value, that makes the file 16 bytes longer, or the text that you're sending 16 bytes longer. This is not usually a problem, but it can be. Imagine you are encrypting a file. So, okay, you have the file on the disk, and then you click the button to encrypt it. Under Microsoft Windows, if you right-click a file, you can say, I want this file to be encrypted on my hard drive, and it will encrypt it and store it there. Of course, if you're using secret key encryption or any encryption algorithm that's stream encrypted, and of course we want to use stream encryption and not the electronic cookbook method, then it gets a little bit longer. Well, it might be difficult to store the encrypted file in the same place you had the non-encrypted file, because now it's that little bit longer. Some systems put the initialization vector in the file's table of contents so that it can be retrieved by the system, but it's typically not value seen by the user, and it's not stored directly with the text.